Yeah, okay, welcome back everyone. So today it's our pleasure to have Nisha, who will be talking about two-word physical generative models. And yeah, so this is possibly the last one for this academic year. And yeah, so it's our pleasure to have her here. Yeah, thank you. Thanks, Nisha.
Hello, everyone. It's nice to see many people. Thank you for joining. And thank you, Bhumidian, for inviting me. So today, what I'll be talking about. Oh, also before I begin, I'll please feel free to interrupt me at any time if something is not clear. I plan to go very slowly because Bhumidian told me this is a very informal style and people take as long as they want to understand something, and it would be very nice to get your feedback and your questions during the talk as well. And I hope that some of this is useful towards thinking about what I'm calling physical generative modeling, which just means that we want to do generative modeling for distributions with some kind of low dimensional structure that we encounter in physical problems or even in data science problems. And we want to be able to do generative modeling with some guarantees. And towards this, in the talk, I will be asking some fundamental questions. So it will not be very flashy. I won't show you high dimensional generative models, but hopefully the insights that I'm going to share today will be useful towards improving algorithms for generative modeling. Okay, with that, I will start. Okay, so I mentioned that we're interested in doing generative modeling or asking fundamental questions about generative models in the case where the target distribution has some low dimensional structure. So what I mean by that is that we now have widely accepted that target distributions in real life, target probability distributions that we want to sample from, may actually be absolutely continuous or have a probability density only defined on a low dimensional manifold. This is illustrated here where we want to sample from this space of images of dogs, and D bar here, this images from this paper by Pope et al., where they're able to control the latent dimension of the generative model, and they see that if they increase the latent dimension, they say that the intrinsic dimension of the underlying manifold is unrealistically high, then you get something that's meaningless. And if it's just right, you can get a very sharp image of a dog. So really, the number of pixels is not really indicative of the dimension or the intrinsic dimension described by the data, but rather there is some smaller intrinsic dimension and some kind of data manifold, a vague term, where this distribution is supported, and this is of a smaller dimension than the ambient dimension. Now, in scientific problems, which are closer to my interest and also closer to some things I know more about, this is also true. This phenomenon of there existing a low dimensional structure in distributions that we want to sample from. Here is the invariant distribution associated with a chaotic system. What I'm showing you here is the empirical density obtained on a very, very long orbit of a two-dimensional chaotic attractor. So this attractor is technically in two dimensions on this square, this compact set. But the density really is only defined along these curves that you see, which are unstable manifolds of this chaotic system. This is a one-dimensional unstable manifold. And transverse to this, you can see that there's no notion of density. It's a singular measure. So you can think of this really as being supported on these leaves, and in the transverse direction, it is singular. It's like a Cantor set on which this measure is supported. When we want to sample from a distribution like this, really this problem is one-dimensional as opposed to two-dimensional. And this whole talk is about formalizing these results and asking some fundamental questions about them. But before we ask these questions, I just want to say that there are many instances where we want to sample from measures like this. This is not a contrived setting. So for example, if we have some physical problem, here I'm using a geophysical problem as an example. Let's say you have some climate model whose orbits or trajectories are described by this x f of x, f applied 2 times on x and so on. And this is not really visible to us, or there's some imperfect model that we would like to correct. And we make some observations which could be low dimensional about the state. Here x, I'm just writing this as a capital X to indicate that it's like a random variable. And we make some observations, and we're interested in sampling from what is the state or what are the parameters of this f given these observations. And now the claim is that these distributions as target distributions also inherit some low dimensional structure that is present in the dynamical system. So whenever we want to solve computational problems associated with sampling or just generative modeling, which are somewhat two different problems with the same end goal of generating samples from a target distribution, we're interested in how to really exploit this low dimensional structure to make algorithms more efficient and also get theoretical guarantees for these algorithms that they're actually generating samples from the measure that we care about. Okay. So towards this end, the first question we will ask is more broadly about generative modeling algorithms that are based on using neural networks to approximate some part of the measure transport process. And here we will ask, when these neural networks are used, when can we expect that even with mistakes, we're able to sample a target measure that is almost similar to the target measure that we care about. And all this similarity will be made precise very shortly. So this is the first part, which I will be focused on mostly. And this is joint work with a student, Adrian, who is a PhD student at University of Chicago. Then in the second part of the talk, maybe some of you have heard this before since I've given talks on this before, but it will be nice to repeat this here since this is a machine learning and dynamics seminar. This is about learning dynamical systems, but really it's about generative modeling because I want to learn dynamical systems in a statistically accurate fashion. That is, if we learn a dynamical system and we now generate the invariant measure by running the learned dynamical system, when can we get guarantees that it will produce samples from the true physical measure of the dynamical system? I'm going to talk about this in the case of chaotic dynamical systems. And the last part is really, I want to say that for such measures with a low dimensional structure, there are easier ways to learn the score or the gradient log of some notion of density associated with this measure. This would be towards the end. I would just make it as a remark. Okay. So if there are no questions about the outline, I'll proceed with the first part on robustness of generative models. Yeah. Are there any questions? I don't see anything, so I'm going to proceed. So what do I mean by robustness of generative models? This is this is a question that has been created a lot of excitement in the generative modeling community. But here I have a specific notion of robustness, which I'll illustrate with this picture. So let's say we have a target distribution that is supported. This is maybe all of us have seen this before, the two moons distribution. So this is the target distribution, and you can see that it is somewhat low dimensional in that the support of the target distribution is almost on this one-dimensional, these two one-dimensional curves in 2D. And if we take a generative model, in particular a score-based diffusion model, we see that, and then if we add some errors, Okay, so this has been generated by a score-based diffusion, and it has been learned by a neural network. The score has been approximated by a neural network very well, and we obtain the target almost exactly. Okay. On the right, we run the same model, but now we learn it inexactly. In other words, we can add some errors to the dynamics of the process that is generating these samples. And then we get this distribution. And it is striking that this generated distribution with the errors looks similar to the target distribution in that the support of the generated distribution um, contains the support of the target distribution, right? So even with the inexact distribution, you can roughly say where the data are supported, okay? Even if the distribution is wrong. So the high density regions have been shifted slightly. The low density regions are also. So the density on the support seems to be wrong, which is to be expected. We are learning with some perturbations, generating the samples with some perturbations. However, you can still make out that the support of the distribution is present in the generated distribution with errors. We are not the first people to make these observations. Several people have observed that even under errors, certain types of generative models have this property that they're still able to roughly sample from the data manifold. Right? But how do we formalize this notion of sampling from the data manifold? And when can we expect the generative model to have this robustness of the support property? Okay. That's the question we're going to ask. And to answer this question, let's just consider a bunch of samples distributed according to the data distribution. Throughout, this will be the target distribution, and it may or may not have a probability density. And to distinguish the two cases where it has a probability density and it doesn't, we will say that these samples are actually from R capital D, where capital D is like the ambient dimension. So if you're sampling from images, you can think it is the number of pixels times the number of channels per pixel. And the fundamental question in generative modeling, or the goal of generative modeling, is to say, given some samples from the target distribution, generate more samples from the same distribution. And this is, of course, a proliferating field with a lot of really excellent ideas for doing this generative modeling. And one can say that underlying, maybe this is a reductionist view, but underlying these various different ideas for generative models is the fact that you're trying to learn a vector field, which a time-dependent vector field, which I will denote as VT. This is a vector field. And somehow this vector field is used to, this is learned based on some optimization problem, and then it is used to generate samples by taking the probability flow of this vector field. Okay, a bit more concretely, in a score-based diffusion model, this vector field is the score of a noising process. So this is some forward process, typically like an Ornstein-Uhlenbeck or an OU process, which is started or initialized with the given samples from your target distribution. And then these are the scores, and these scores are learned approximately with a neural network. In another set of generative models that are based on flow matching, these vector fields are learned based on a different principle, a different kind of optimization problem. But nevertheless, the idea is to transport probabilities. So this is probability measure transport is the underlying idea. And in particular, they transport a measure P0, which is easy. This one usually has a density to P data, the target. And this vector field is learned in such a way that if you minimize some kind of loss function to learn this vector field, the probability flow of this vector field will be such that in finite time, so P tau, where tau is some finite final time, we recover the data distribution. Okay. So if you take samples that are according to P0, and then you just run this, run an ODE, which I have not shown here, but the ODE is basically dx dt equals Vt of x, xt. Then this ODE will now have a distribution. The samples generated by this ODE will have the distribution P data at a finite time tau. Okay. Pictorially, I guess all talks on generative models have this picture. So here is the picture from this very famous paper by Song and Ehrman, where they recover a very nice sample from this image distribution over dogs by considering some a noise distribution as the source distribution. Okay, this noise distribution is really obtained by doing some forward process starting from data samples. So here is the only thing to note here is that the direction of time is from here to here. So at t equals 0, you are at the noise or source distribution. At t equals tau, you are at the target distribution. And we now want to ask, okay, every generative model is going to have some loss function, right, which is being minimized. Theta are the parameters of a neural network that will represent Vt, the true vector field. But the true vector field is going to be approximated by, say, Vt theta, a neural network representation of the vector field. So how do regression errors in learning this neural network propagate along the dynamics? Okay. The dynamics that generates these samples. Okay. And based on this propagation of errors, can we distinguish two generative models and say one is more robust to errors in the regression than the other? Okay. To answer these questions, let us take a dynamical systems perspective, which means that we have to start viewing all kinds of generative models as this title says core generative models, but really we are going to say any kind of generative model, even the ones based on flow matching, as a dynamical system. Okay, so in a score generative model, the reverse process is going to be our dynamical system, and the reverse process is a coupling between some P0, which has a density rho 0, to P data that may or may not have a density. So we'll say it has an approximate density rho tau. Okay. The generative model itself is a sequence of steps. Okay. And each step is time dependent. So the dynamics is non-autonomous. And there can be randomness if you take a generating process to be a stochastic process, and there is no randomness if it is a deterministic process. But it is always going to be non-autonomous, since the dynamics at each step, here denoted as F with a subscript T, is time dependent. You can think of at each time we're choosing a dynamical system according to some probability density or probability measure pi t on the space of dynamical systems. Okay. So the randomness here is represented like it could be a Wiener path, that's why the W. And you can think of this randomness as if you fix the Wiener path, then it becomes just a non-autonomous deterministic system. And we are considering discrete time to represent directly the generative modeling algorithm itself as a dynamical system. So you can think of each step as the time integrated ODE that we looked at before. More concretely, for a score generative model, if you just use Euler-Maruyama, and here is the score, which is supposed to be a neural network, and then this WT is just some IID standard normal random variables to represent time integration of a Brownian motion. Okay. Now, without the W, you just have a deterministic sampler. That's also fine with the same, which will have the same marginals and therefore can also give you samples from the target distribution at finite time tau. I hope you have seen this before in talks on generative modeling or the papers on generative models. For the purpose of this talk, we are going to consider all kinds of generative models as a Markov chain, really, whether or not you have this W with its own transition kernel, and then the transition kernel kappa T it has a density PT. Okay. But if you haven't seen this before, don't worry about it. The important thing to note here is just the definition of this operator LT on densities. Okay. This is usually called the transfer operator in the dynamics literature. It just tells you if the density at time t is rho t, then the density at time t plus 1 is rho t plus 1, and it is given by, if you know the transition kernel, just the integral of something. So it's a linear operator applied on rho t. Now, finite time definitions. So if you're from a dynamics background, which many of you are, you may know that random dynamical systems is now a very mature discipline with a lot of both classical results and then more modern results. But here we don't use asymptotic theory as much, just because we only have a dynamical system that is defined for a finite time. So our dynamical system here, our generating process, is only defined from 0 to tau. Yeah. But there are many classical works that form the foundation of the questions and the answers that we're going to use, the techniques we're going to use. Just as very brief primer on how we are going to study this generating process. Remember that the ultimate goal is to study how errors in the regression evolve along this generating process. And so we care about how perturbations of non-autonomous systems affect the probability density of the samples generated by the system. So on sample space, this is our notation, Ft, which is some diffeomorphism at time t. And then we're going to consider DFT. So this is just the basic idea behind linear perturbation analysis of dynamical systems is that we consider how perturbations or vector fields evolve along linearizations of the dynamics. That is, if you consider starting at x or starting at some x plus some perturbed value, if you perturb x in the direction of the vector field ut, then if you apply now ft, the vector field ut now becomes a new vector field, ut plus 1. That tells you how after one step, the state has moved in the direction of ut plus 1 in the limit of infinitesimal perturbations. Okay, so this is just tangent linear dynamics, which many of you may be familiar with. Okay. And on probability space, as I mentioned before, we have the push forward operator, which you may know as simply, this notation just means that if you take a sample according to PT and you apply the map FT, then you get a sample according to PT plus 1. Okay. PT is the probability measure, rho T is the associated density, and we can define the transfer operator, which simply takes a density. As I mentioned, it's a linear operator, and this is also a time-dependent transfer operator because we are in a non-autonomous setting. Okay. So these are the main objects, linear perturbation analysis. So DFT, simply the Jacobian matrix, and it evolves vector fields. It's a linear operator. And this linear operator on densities simply evolves densities along the dynamics. Okay. So now, if we want to model errors in the dynamics itself, so instead of Ft, at each time we will consider Ft epsilon, and we will let epsilon tend to 0 to indicate very small or infinitesimal perturbations to the dynamics. Under this, we will now get a perturbed dynamical system or a perturbed generative model, which after time capital T, after time T is the composition of the perturbed dynamics at each time. And we can also evolve errors. It looks exactly as before, the errors or the tangent equation, except that there is another term, chi t, which comes from the perturbation of the dynamics. Okay, so this is exactly like a tangent equation, but with an additional forcing that tells you at each time what is the additional perturbation to the dynamics. Okay. Now on probability space, the transfer operator is actually going to change as well because the dynamics have changed. Okay. So at each time, instead of the measure PT, we have the measure PT epsilon, which will now be pushed forward by FT epsilon. Again, we can define now a perturbed transfer operator, LT epsilon, that will tell you how densities evolve under FT epsilon. Okay. Are there any questions about just the setup? So here's the generative model and perturbations of generative models. Okay. Okay. So
yes, I have a question in page 8.
Yeah.
Yeah, so I didn't get you very well when you define the operator LT. And the PT, what is it? And the rho T?
Yeah. So the PT is the density of this kernel, kappa T. So you can simply think of this as this is the probability density of being at state at the point y at time t. And this is the probability density, conditional probability density, that the state at time t plus 1 is at x, given that the state at time t is y. Okay. So this is simply telling you that the density at time t plus 1 is, this is total probability basically, that this is the conditional density of being at state x given y times the probability of being at y at time t.
Yeah, so basically this you are considering in the spirit of generative, more like we are adding noise on the sample data we have at each step so that we're going to get the noisy data. So so the T is the time of adding noise, right?
That is exactly right. Yes.
Oh, okay.
Except I'm looking at the reverse process. So we're removing noise.
Okay. So you're doing backward. Okay, thanks.
Backwards. Yeah, that's exactly right. Thank you for the question. Sorry if there are any more things I can clarify.
Yeah, thanks. It's okay for me. Thanks.
Okay, perfect. Thank you. Anyone else with questions? Okay, so I will move on. So yeah, so now we want to, as Reagan was pointing out, we're looking at the reverse process of a score generative model, or just when there's no reverse process, like in flow matching algorithms, the generating process. So I'll just use the phrase generating process. That is our FT at each time and the compositions of our FT. Okay, we've also introduced errors to this process. Why? Because we want to model errors in learning the vector field VT. Remember that the vector field VT in flow matching is the vector field that transports the source to the target distribution. And in the case of score generative model, this is the score of the forward process or the reverse process. So if you add some noise to the vector field as a model for the errors made by the neural network in approximating the true vector field, then the dynamics are also going to change, right, at each time, because it's simply the time integration of the vector field over a short time. And so that is what we indicate as FT epsilon. And as I discussed, this also changes the transfer operator, where the Frobenius operator, it makes LT go to LT epsilon. Now the question we are all asking is, how does this change the predicted distribution? Instead of running FT, if you run FT epsilon, then you're going to get some rho tau epsilon. How close is it to the target distribution? Okay. Now, if you assume for a second that the target distribution does have a density, or this rho tau is approximately the density, think if you don't have a density, convolve it with a small Gaussian and then Gaussian of small variance, and then you will get rho tau. Let's say that's rho tau. Under the assumption that it has a density, we can derive the change in the predicted distribution. Now I have this equation in here with the W to indicate that you can do it even for a stochastic generating process. This W is the Wiener path, but for every path, you can make this statement. But because the marginals are the same, whether you do stochastic sampling or deterministic sampling, I'm going to ignore the W. And we can say that this is the result. The result is that the derivative of the predicted density, so this is rho tau epsilon at the time x tau, with respect to epsilon. So this is going to say, for a small epsilon, this is like rho tau epsilon minus rho tau 0, which is the unperturbed, which is close to p data, divided by epsilon, is going to be this. So this is the error in the predicted density. And you can see that that is supported only on the true target density. Okay. So in the case of infinitesimal errors, pretty much for any wide class of generative models, as long as they satisfy some smoothness assumptions on F, we can show that there is the change in the predicted density is supported only where this is supported. So when this is 0, the change is 0. When this is non-zero, it can be non-zero. And it's just this density multiplied by this whole scalar term that depends on the score and this chi t, which is the error vector field. Okay, so this is just an exercise that we can do with just some integration by paths. But it is nice to have this property that really only where the support of the true target distribution is 0, that's where we will see errors, as long as we make small infinitesimal errors in the learning process. Okay. Now we can go further to ask exactly how to characterize these errors. Okay. So we can ask, if this applies for all generative models, then how can we distinguish two generative models based on how robust they are to errors, how robust the support of the predicted distribution is to the errors, right? If you add errors to the generative model, of course, there are errors in the predicted density, but really what we care about in this talk is how robust is the support of the predicted density, not the predicted density itself. Okay? So I just want to make that very clear. We just want to say vaguely that it is sampling from the same support, even if the density on the support is incorrect because of errors in the regression. So here are experiments with the diffusion model. So on the left, you see a model that is pre-trained. This is actually Yang Song's code on GitHub. I just used the pre-trained model. So this is a pre-trained model on the CFAR10 data set. This is the unperturbed model. This is a model with the perturbations. Okay. You can really visually not see any difference, even if you add errors. And these are order 1 errors, even big errors, to the generating process. We still get some realistic looking images with these score-based diffusions. And you can calculate the FID score, the likelihood, and so on, and they match quite well, like they're close to each other. So you can't really tell that the quality of the image has gone down when we add the errors to the reverse process. Here is another example that seems to be less robust. This is this 2 moons example, low dimensional example. So I don't know if this holds for high dimensional images. For low dimensional example, the target distribution here is this 2 moons distribution that is generated very well by this conditional flow matching algorithm. This is also from a code by Tong from the optimal transport conditional flow matching paper. So I should have put the reference here to the GitHub links. And then here is a model where I just added a perturbation to a model that generates this. And then you can see when the perturbation is order 1, you get something which looks very much unlike the score-based diffusion model that we saw before, where you could still see robustness of the support, but here there doesn't seem to be robustness of the support. You can't tell that the support is this by looking at the perturbed distribution. Okay. So naturally, we want to ask the question, so clearly these 2 generative models are doing different dynamics. So is there something about the dynamics that leads to robustness of the support under perturbations in one case and not in the other? Okay. To understand this, we will again go back to our tangent space equations and now define what is called a sensitive subspace of the tangent space. Okay. These are like finite time versions of Lyapunov, if you know some oscillated theory of Lyapunov vectors. Okay. But because these are finite time dynamics, I'm just defining finite time backward Lyapunov vectors. So again, consider the originodynamics, Ft, which is a composition of the time-dependent FTs with the subscript T. And then you remember the tangent dynamics is the same thing as before, but now I have written is ET to represent a subspace. Okay, so you can think of this as a capital D times small d matrix, where small d is the dimension of the data manifold. Okay. Or a guess for the dimension of the data manifold. The small d can be anything less than capital D or equal to capital D. Yeah. So if this tells you the propagation of errors along subspaces. Okay. If you randomly choose a E0, a matrix E0, so random subspace, and then you evolve this, let us define, this is the definition of ET plus 1. It's a recursive definition. So if you apply DFT, this matrix to ET, and do a QR decomposition, this is the definition of ET plus 1. So ET always consists of orthonormal columns, and it is going to represent the most sensitive subspace under the dynamics of the tangent space, because you're constantly multiplying by DFT. So by an argument very similar to power iteration, you can think of ET as representing the direction where any errors would have grown the most. Now, if the dynamics is entirely stable, this is still the most sensitive, okay, subspace. Of course, this definition is itself, this is like a Gram-Schmidt procedure to calculate the oscillated subspaces or the subspace of backward Lyapunov vectors. But this is only true if you take infinite dynamics, and there are extensions of classical oscillated theory for autonomous systems to non-autonomous systems. But this whole thing is finite dimensional. This is just a recursive definition. That's why I'm calling it a different name. Just call it sensitive subspaces. Okay, and there is a history of using these sensitive subspaces in physics. In hydrodynamics, for instance, and lots of applications in geophysics as well, where they call this DFT. Notice this is a superscript. So this is a product of the Jacobian matrices times Jacobian matrix transpose. The eigenvectors of these matrices, this matrix is called the Cauchy-Green tensor, and the eigenvectors are used to study deformations of fluid flow in hydrodynamics and in especially in geophysical problems. Okay. So with the definition of this E0, we hope to answer our question, not E0, sorry, ET, recursive definition of ET, these most sensitive subspaces, we can try to understand what distinguishes two generative models. How can we get information about the robustness of the support property by looking at these sensitive subspaces? Okay, because these sensitive subspaces are easy to compute because I've just defined them constructively, and DFT is the derivative of the generative model, which is very easy to obtain because it's a neural network and you can do automatic differentiation. So you can actually compute these subspaces. Yeah. And I should mention that this R from the QR decomposition, it consists of finite time Lyapunov exponents. In particular, if you look at the diagonal elements of R and take their logs, the average over time are what are called finite time Lyapunov exponents. Now, what do they look like? I'm just, for visualization purposes, consider the target distribution being on this nice curve in 1D. And this is a smooth curve in 2D, in R2. Okay. Here is the target distribution shown as contour plots. This is a real target. And this is a perturbed target. You can see that the support is still maintained. This is run with a diffusion model. And correspondingly, these red lines shown in the background of the target distribution at specific points is this most sensitive subspace. So this most sensitive subspace is the top most sensitive subspace, so only one dimensional. And you can see very nicely that it seems to be aligned with the data manifold or the support of the target distribution. Okay. And this is not just an empirical observation for this particular target. It seems to be universal whenever your support is maintained under perturbations or there is robustness of support. We also started observing that the most sensitive subspaces seem to be aligned with the data manifold. Okay. So then we sought to understand this better, and then we came across a whole range of works, all of which have made similar observations, except not with the sensitive subspace, but there are different perspectives on understanding how diffusion models learn the data manifold. Okay. This work proposes that because of score blowup, Yakiv Pichtigach showed that because of the score being unbounded is a necessary condition to learn the data manifold. Okay, and talks about memorization versus generalization of generative models. This work by Stanchuk et al. Published last year looks at the data dimension, the intrinsic data dimension being reproduced by score generative model. One can learn the dimension of the intrinsic manifold by a score-based generative model. There are other works by Chen who also look at this and so on. And here we sought to ask, now we have this interesting object, these most sensitive subspaces. Can we say something more about exactly what about the data manifold a generative model is learning? And does every generative model learn this information about the data manifold? Okay. So the first result in this direction that uses these most sensitive subspaces, I'm going to state it informally. For this, we will assume that the target distribution actually is singular. So it has a low dimensional support, which is denoted here as M, this manifold. And it is a small d dimensional manifold in RD, R big D. Yeah. So the most sensitive subspaces, if they are aligned with the tangent spaces of M, okay, we will call such a generative model aligned. Okay. This doesn't have to hold at, this only has to hold at time tau. Sorry, this is my bad. E tau should align with the tangent space of M. This is at final time tau. Okay. Now what we can show is that if this alignment holds, then the generative model learns the support of the target distribution. Of course, the generative model has to be convergent in the sense that as epsilon, the error goes to 0, error in the generative model goes to 0, you recover the target distribution. So several theoretical works have shown convergence of all these different ideas for generative models. And if we take a convergent generative model that additionally has this alignment property, which uses our most sensitive subspaces, a d-dimensional subspace where the errors are going to grow the most. If the errors are going to grow the most in the tangent space, so this is perfect alignment, tangent space of the support of the target distribution, this is the situation where you can claim that the generative model learns the support of the target distribution. Now, what does learning the support of the target distribution mean? It means that we can use the samples from the inexact generative model, okay, so the perturbed generative model, and we can learn a binary classifier. So we can say that if we a one class binary classifier in the which is going to say give you 1 if you're on the support and 0 if you're off the support. If we can use the generated samples to do this with high probability, then we can say that a generative model learns the support of the target distribution. So to prove this result, we just say that such a classifier exists. Okay. If such a classifier obviously exists for the unperturbed or the original generative model, by assumption, because we've assumed that the generative model converges. So if you make 0 errors, then it can recover the target distribution. Therefore, it can recover the target support as well. But then if the most sensitive subspaces are aligned with the tangent space of the manifold, if you know some classification or margin theory, which is a classic or part of binary classification, maybe you've studied this in a machine learning 101 class, the margin of a one class classifier does not change if you move points tangent to the hyperplane. And that's all we use. So we just say that, okay, if the alignment property holds, it means that you're simply moving points because these are the most sensitive subspaces. This is where the errors will be made. And you're simply moving points along the hyperplane, does not change the margin of the classifier. So the same statistical bound should hold. Okay. So in this sense, it seems that if we have an aligned and convergent generative model, we can learn the support of the target distribution provably. So before I move on to some numerical results to visualize this, are there any questions?
Yes, hi. I have a quick question. I like this approach. So is there a way to turn this somehow into not a criterion, but a way to design a generative model? So if I have a data manifold where I know where the tangent space is, right?
Yeah.
Can I make the alignment as a criterion to design a generative model that will actually maintain the support?
Yeah, thank you for the great question, Panos. This is why I'm excited about it. This is what I'm thinking about currently, actually, and I would welcome any ideas.
Yeah.
Like I said, these tangent spaces are very easy to compute, and it would be fantastic to be able to steer the generative models in such a way that they're going to be aligned. So we always produce some plausible samples, even if we know that the density on this high dimensional manifold is incorrect. We still know that these correspond to a plausible climate or like a plausible molecular configuration or something, right? That would be very nice. Yeah, so I think this would be like a control problem. One can
Right.
pose this as a control problem to produce alignment.
Right, because he said that you can compute the capital ET, right?
Yes.
Because you have, so, and then if you have, of course, the tangent space of the data manifold, which in high dimensions is not going to be an easy thing, But then you can use that as a criterion to train your score function, right? So to put alignment as part of your loss function, I don't know, something there to enforce it somehow.
Yeah. That's
And
actually
it will not, sorry, it will not guarantee when you use it that it will actually do that, right? Because when you enforce it during training, it doesn't mean that when you use the model to do inference, it will always satisfy this. But at least if you can enforce it during training, you have a higher chance, right? Of
Yes. Absolutely, I agree. It would be very nice to look at various algorithmic implications, how to impose alignment.
Right.
The only maybe one helpful result I have in this direction is that it looks like score-based diffusion models are automatically aligned. So
Okay.
interestingly, so here I'll show you a numerical example. I already showed you with the CFAR 10, I didn't show you the computations of the vector field, but in this MNIST data set, we have some numerical results. So here is the MNIST data set starting from some noise distribution. So on the left, you see this sample from a noise distribution. The second image is the predicted image with the original pre-trained generative model, score-based diffusion generative model. Okay. The next image is actually this image plus a perturbation. So this image plus the most sensitive Lyapunov vector. So I think this is like an order 1 perturbation. So you take this and walk along the most sensitive Lyapunov vector, which we computed for the original dynamics. And you see, it actually still looks very much like a 4, right? So it means that this is still on the same manifold, hopefully. And this next thing is this image plus the 100th most sensitive Lyapunov vector. Clearly, because the intrinsic dimension of the manifold is around 15, many people have calculated this before, that the MNIST data set is actually very low dimensional. Intrinsic dimension is around 15. So if you take something that is obviously much greater than the intrinsic dimension, you get something for the same size of the perturbation, something that no longer looks like a digit. So this is off the manifold, right? So if you take the score generative model and calculate this inherent property of the dynamics of the score generative model, which are these most sensitive Lyapunov vectors, it looks like they're learning the tangent spaces of the intrinsic data manifold. You can also see this. Yeah. And you can also see this in the Lyapunov exponents as well. So here are the Lyapunov exponents. They all happen to be stable. And these are finite time Lyapunov exponents. And here is the index. So the real size, the ambient dimension for the MNIST is, as many of you know, 784, 28 times 28. But you see that there is a small gap in the Lyapunov exponents right at the point where we believe is close to the intrinsic dimension of the manifold. Okay. So these are less stable compared to this whole band of Lyapunov exponents that are more stable. Okay. So the least stable or the most sensitive Lyapunov exponents and the corresponding Lyapunov vectors contain information about the data manifold. That's the claim. Okay. We can now ask, okay, this seems to qualitatively agree with what we said, right? Can we also get sufficient conditions for when exactly to expect alignment? Okay, this holds for score generative models. Can we say it holds for some other kind of generative models? This seemed like a very tricky question. We could not get necessary conditions, but we could only get sufficient conditions. So one sufficient condition for when this alignment property, which recall is that the most sensitive subspaces as we defined before are aligned with the tangent spaces of the data manifold. This happens when we have the original dynamics, this F tau, which is the generative model from 0 to tau. This is compressive overall. That means all the Lyapunov, finite time Lyapunov exponents are negative. And this VT, the vector field, is uniformly compressive. Okay. And it has small cross derivatives. So it seems like a lot of technical conditions. Intuitively, what this means is that if you have a very strong attracting force to the data manifold, then you get alignment. Basically, there are very stable Lyapunov exponents corresponding to just getting attracted to the manifold, which seems intuitively when we would expect that you have extreme stability of going towards the manifold, normal to the manifold. So errors, if you make them, are automatically going to be tangent to the manifold. Okay. How we can show this is to look at the evolution of the scores. These are the time scores. Okay. As we know, if the target distribution is singular, then S tau is unbounded. The score is unbounded when your target distribution is singular as t tends to tau. But if you project the score on the most sensitive subspaces, we are asking, when does this not blow up? Right? Because the score components tangent to the data manifold do not blow up. It is the score components normal to the data manifold that blow up. Okay, so we can write down a recursive equation for what this evolution of the score components along the most sensitive subspaces ET look like and derive conditions for when this will be arbitrarily small. So if the score is normal to this ET, then we know that the ET has to be tangent to the data manifold because the score blows up in the orthogonal direction. So it's really pointing towards the orthogonal. S tau is orthogonal to the data manifold. So if S tau E tau is 0, S tau dot E tau is 0, then that means that E tau should be tangent to the data manifold. Okay, so that's how we derive these conditions. Now, if you look at this, it depends on R tau, and it contains this RT inverse, which consists of the Lyapunov exponents. You can really think of this RT as how much the volume has compressed or expanded at time t under the tangent dynamics. Now, what we know about this thing is that if RT is actually expansive, if determinant of RT is greater than 1, you can basically show that this goes to 0. Okay, this is what happens if you have some time-dependent dissipative dynamical system. But empirically, we observed that for most of these generative models, we could not see a lot of expansion. Maybe there is some expansion for some orbits, but not for all orbits. So that's why we assumed that the dynamics is compressive overall, and we can still get some sufficient conditions under which this holds, alignment holds. Okay. Numerically, we can see this with examples. Here is around t equals 0. So short times, this is what the distribution, this is like a noise distribution. This is the target distribution for a diffusion model. And you can see that the scores are all pointing, inward. And at time tau, the cross derivatives of the score or the vector field are 0. They're close to 0. If you squint, you can see that basically when the score is changing, let's say the y component of the score is changing along y, the x component along the score is changing along x, but the x is not changing so much along the y. Okay? So this seems to satisfy intuitively the sufficient conditions that we have, but there's way more work to be done. And maybe it's more interesting to actually ask algorithmically in practice, when does this hold and when does it not hold? Okay. And then, of course, when these sufficient conditions seem to hold, and we do seem to get, if we calculate the most sensitive Lyapunov vectors, they seem to be nicely aligned tangent to these directions, tangent to the data support, and then therefore under perturbations as well, we're able to sample almost from the same support as the target distribution. Whereas we calculated for these low dimensional examples, conditional flow matching, optimal transport conditional flow matching, and these are stochastic interpolants. which are all based on an idea, like the underlying idea of flow matching, which I've since learned maybe does not have this property in high dimension. It is robust in high dimensions, but somehow in lower dimensions, I was able to see that the robustness is probably not there. So to illustrate that, what I'm showing you here in red are the topmost Lyapunov vector. So this is the most sensitive subspace, which is just one dimensional in this two-dimensional example for 3 different algorithms that is shown in red at each point. And in blue, we show the score of the data distribution, okay? So if these two are perfectly orthogonal to each other, that is the angle between them or the dot product is close to 0. This is the histogram of the dot product of the target score and the most sensitive Lyapunov vector in each of these different algorithms. In the histogram, you can see that this model seems to be the most aligned OT-CFM, optimal transport conditional flow matching, compared to conditional flow matching and stochastic interpolance. And it looks like this is how the robustness also behaves, that this is more robust than this and this. Yeah. I will show you now for the histogram of the dot product. So this is really a proxy for alignment. So for alignment being more, you get more robustness. So this is a perturbed distribution of the 2 moons data set. And this is again a perturbed distribution with epsilon equals 1 for conditional flow matching, which looks non-robust, and stochastic interpolance, which also looks non-robust. Okay. Are there any questions? So to summarize what I've said so far, it looks like the alignment of the most sensitive Lyapunov vectors with the tangent spaces of the data manifold is one way to think about getting robustness of the support of the target distribution. This does not mean that a generative model with errors will still give you the correct distribution. It only means that it will give you samples, or it is able to provably learn the support of the distribution. Okay, we can show that even if your generative model has compressive dynamics or expanding dynamics, you can get sufficient conditions for getting this alignment property. And even though this alignment is only sufficient, there are other ways maybe of getting the robustness of the support. All of these things are just characterizing sufficient conditions. Okay. But the real important point, maybe this is not the best way to do manifold learning, but it is interesting that when you have alignment, generative models that are probably going to sample from the support, that is, they're convergent, probably going to sample from the target distribution. These are manifold learning algorithms. That is, they can learn the tangent spaces to the data manifold, and you can compute them easily by doing this QR-based algorithm that I showed. Okay. And finally, here is a small result that basically says that if you have alignment, a perturbed generative model will also have alignment. Whenever we discuss a property, maybe we want to say under perturbations, does the property still hold, right? And this property does hold. That is, if you have a score generative model which has this alignment property, a slight perturbation of the score-based generative model will also have the alignment property. This is a kind of just an analysis technique to prove this. Okay. If there are no other questions, and if people still have enthusiasm, I can talk about learning dynamical systems, or I'm just happy to stop here and have more discussions and questions.
Yeah, I think feel free to continue, I think, yeah.
Yeah, okay. Thanks for the support. Sorry, I've been talking for too long.
No, this is good. Yeah, as I told you, there is no time limit, and then the talk is recorded, so people who want to leave, I mean, they can always watch the recording later. Yeah, thanks.
Yeah. If anybody wants to leave, please feel free to leave. Okay, so in this part, I want to talk about learning chaotic systems in a provable manner. That is, we want guarantees that if we learn one step of a chaotic dynamical system, we are going to, oh, I think there's a question. Oh, thanks for that. Okay. The setup is as follows. Here you have an autonomous dynamical system, F. This is our true dynamical system. So you can think this is one step of a climate model that is chaotic, let's say. So that is F. And we have pairs xt, f of xt. And let's say we approximate this with a neural network or with a kernel method that Boumediene has done a lot of excellent work on. Let's say we have some model that approximates this one-step dynamics. And then we can ask, can we also ensure that the learned model is physical, in the sense that if you now run the learned model autoregressively, can you sample from some, say, mu, which is the underlying physical measure of the chaotic system? Okay, I will tell you what the definition of a physical measure is very soon. But this is some natural measure associated, probability measure associated with the dynamical system, which ensures that long time or statistical accuracy of the learned model. Okay, so we know how to learn surrogate models. We will say, take some loss function. For the sake of analysis, we'll just consider the simplest case where we don't know anything and we just use mean square loss to learn one step. So we take samples from mu, and then we learn this with we do empirical risk minimization with a mean square loss. You can also think of this dynamical system as actually coming from a short time integration of a continuous time dynamical system, like a neural ODE. So we will train when test errors are small, we will be satisfied. Here are some loss functions as a function of epochs for just the Lorentz 63 model. Okay. And we calculate the Lyapunov exponent, so the learned model, which is supposed to have good generalization error. Oh, sorry, I forgot to define generalization error, which is defined as this loss function averaged over the true data distribution. Is there a question? We're not seeing the slides. I see. Is no one seeing the slides?
No, I see the slides.
Yeah, we can see the slide.
Yeah,
I think it's his problem. He should check his computer.
Yeah.
Oh.
Yeah, Manjuna, we see the slides, yeah.
I see. Maybe you can, oh yeah, no problem. Maybe if you rejoin, you can see the slides. Okay, so I'm going to continue. So we have the generalization error is simply defined as an expectation of the loss function with respect to the true distribution, which is mu. As a proxy, we approximate generalization error with the test error, and these models have acceptable test performance, right? So we can just wash our hands and give up. But then if we feel adventurous, we can compute the Lyapunov exponents. At this point, you should just think of Lyapunov exponents as some kind of statistical measure, an inherent property of this chaotic system. Here I've taken the Lorentz 63 system, and you can see, okay, you have these Lyapunov exponents. These are the true values. And these are the values computed with a neural ODE, which is supposed to have good generalization error. It is good. It's a good model. But you see that it is not predicting the Lyapunov exponents correctly. Okay. As a result, if you take a random orbit of a neural ODE that is learned with low mean square error, so MSC res stands for mean square error, trained with mean square error, and it's a ResNet. And if you take a random initial condition, this is what the true dynamics is supposed to do, but you can get something unphysical, like going off the attractor, coming back, and so on. Okay. However, we noticed that if we add some term, which in addition to minimizing the mean square error of the dynamics itself, also minimizes the difference in the Jacobians. So this is the Jacobian matrix, same notation as before. This is a Jacobian matrix of the neural network, Jacobian matrix of the ground truth. If you minimize this distance, I think this is just a Frobenius norm, then you get, now if you calculate the Lyapunov exponents, they seem to match the ground truth. Okay. It was not just the Lyapunov exponents. We can calculate any kind of statistical measure. We can calculate the time averages of various quantities. We can calculate correlations. All of them seem to be accurate. So it's truly learning the Lorentz system in a statistically accurate manner. Okay. What do I mean by that? This mu, sorry for defining this late, is called the physical measure. What this means is if you take almost every orbit for almost every initial condition, so this is Lebesgue almost every initial condition. If you take a ball around the Lorentz attractor and start almost anywhere, then, or with any probability density, this is going to converge as t tends to infinity to this measure weakly. And this, such a measure is called a physical measure, and there is a unique physical measure for this Lorentz 63 system. Alternatively, if you take, or equivalently, if you take any function j, which is an observable, and you let t tends to infinity, then time averages, finite time averages, oh, this should be capital T, I apologize, tends to the expectation with respect to mu. Okay. Now it looks like with the Jacobian model, we are able to learn the physical measure because all statistics with respect to the physical measure are being reproduced. Okay. So here I'm showing you once more. Here is the probability distribution of one of the variables, I believe the x component of the Lorentz 63. That is reproduced very well by the Jacobian model, not reproduced well with the mean square error model. So then we can ask this question, is this always enough? Okay. To get a good generative model for a chaotic system, can we just learn one-step dynamics with the Jacobian laws, and can we always ensure that this is true, that it is statistically accurate? Okay. Instead, can we just do generative modeling of the physical measure directly, right? Like we have shown with that it is possible with score-based diffusions or something. So to answer these questions, what we can show, I'm going to be a bit quicker. I'm just going to say the result directly. We can basically show that if you generalize well, that is, if this error is small and the loss is the Jacobian loss, it also includes the Jacobian matching term, then you can show that there is some finite time shadowing property or a probabilistic version of the shadowing property holds with high probability. A probabilistic version of the shadowing property holds. Okay. For those of you who are familiar with shadowing, if you're not familiar with shadowing, don't worry about it. What this means is this is a classical notion in dynamical systems theory that tells you when two orbits of slightly different dynamical systems are close to each other. Okay. If you have a perturbed dynamical system like a neural network, FNN, and it's generating some orbits, shadowing holding means that there is a true orbit, an orbit of F that lies close to an orbit of FNN. Okay. So then if the shadowing orbit distributes according to mu, the physical distribution, then so does the close orbit of FNN. That's the idea. The idea is basically that classical proofs of shadowing do involve C1, the origin on the perturbed dynamical system, being close in C1 norm. And this does happen if you train with Jacobian laws. With high probability, this happens. And therefore, we can get with high probability shadowing. but you cannot get guarantees of shadowing for just training with the mean square error. Okay. So informally, this basically says that if you train a model that satisfies C1 strong generalization, that means you generalize well with the Jacobian laws. And additionally, there is an assumption which may or may not hold actually in practice, which is that the shadowing orbit distributes according to mu with high probability. Then you can show that the Wasserstein distance between the learned measure, this is the empirical measure generated by an orbit of the neural network, is close to the physical measure. So there is some kind of theoretical guarantee for why this works for the Lorentz system, and hopefully this is universal whenever you have typical shadowing or shadowing orbits distributing according to the physical measure with high probability. Okay, this hopefully explains why we are seeing this hold across architectures or different surrogate models. Whenever we train with the mean square error, we see that statistical metrics, here are 3 different statistical metrics, all of them are lowest for every architecture if we train with the Jacobian laws when compared to mean square error. We also see this hold beyond the Lorentz system. Here is a KS equation, which is supposed to be a prototype for turbulence. And here are the solutions of the KS equation shown over X and time. The original one, the mean square error one, that diverges somewhat unnaturally from this because the Lyapunov exponents are not matching. And here is a solution from the Jacobian trained model. Jacobian loss trained model. We can do this for other systems, Rossler. There are many examples in the paper. I'll share the link. And in all, for the KS equation, for example, we find that if we train with the mean square error, we only get 2 out of the first 64 Lyapunov exponents predicted well. But whereas for the Jacobian loss, we get most of the Lyapunov exponents predicted well within 10% error. Okay. So it's just a small result that tries to explain why even if we are learning with only one step of the dynamics, it seems that we can get statistical accuracy if we also know the derivatives of the dynamics. And this is true under some conditions. Okay. And finally, I want to leave you with a remark. Sorry for talking for so long. I'll leave you with a remark about really getting generative models for chaotic systems with guarantees. I'm just going to leave you with a remark that is hopefully useful in training generative models for invariant measures of chaotic systems, physical measures of chaotic systems, as we have discussed so far. Okay. Now, in the generative modeling problem, as we have discussed before, there is some target measure nu. Sorry, my notation for the target measure keeps changing. For now, it is some nu. When we are already given samples, right? But the sampling problem, essentially we want the same thing. We want samples from nu, but what we're given is the score of the target distribution. That is the gradient log of the density associated with the target distribution. Now, if we really want to sample from an invariant measure of a chaotic system, this quantity does not exist because A, there may not be a density. B, what do we define as the gradient, right? Like there is a density, but it's really only conditioned on the unstable manifold. So we need to change the definition of the gradient. Okay. But the underlying idea is that even when you're doing generative modeling, we're still going to approximate the score somehow, or this quantity is essential. So I want to make the case that if we have a way of computing these scores, perhaps we should use this to make generative modeling algorithms faster and sampling algorithms faster. Sampling being different from generative modeling only in terms of what we are given, the score. And what we want is exactly the same, samples from the target, so that we can do Bayesian computation, for instance. Okay. So to understand this idea of how to compute these scores and how to exploit this for dimension reduction of generative models, let's just consider a general setting where we have some source distribution. Source distribution, deliberately I've used the same letter as the physical distribution, mu. If it has a density, then it is rho mu. And the target distribution with the density rho nu. Okay. If this is the type of setup, and we want some kind of generative model, that is, we want a transport map which takes the source distribution to the target distribution. I switched the order, sorry. This is the source, this is the target, and here is the transport map, okay, that pushes forward the source to the target. And the score, as we've defined before, is the gradient log of the density. As I mentioned, in Bayesian computation, if we know the score, then we are in luck. We can use any kind of sampling algorithm, including modern sampling algorithms that are fast, like variants of standard variation of gradient descent. There are more recent ones, Fisher-Rao flows and so on, which can do finite time sampling, but they all use some information about the score of the target distribution. Okay. In order to use the score of the target distribution, let's start with the basic operation of where you have a transport map that you're trying to learn. But it satisfies this change of variables equation because it takes rho nu to rho mu. Okay, this is of course only when both have densities, but I'll get to the case where we don't have densities for the target. Okay. So if this is of course the starting point for deriving all kinds of transport map based sampling algorithms. For the moment though, if we take the log on both sides and differentiate it, we can now define an operator that I will call the score operator that takes a score and a transport map, this is the argument u, and gives you the score of the transported distribution. This looks like a hairy expression, but basically you just take log and take the gradient, you get this. Okay. The claim is that if you have a target distribution, S mu, and your dynamics is the transport map, S mu is the score of the target distribution mu, and if mu is actually an invariant measure, so I'm no longer assuming a density, okay, but I'm using exactly the same change of variables and the score operator that was defined using densities and the change of variables formula from here. Okay, I'm now going to derive a different version of this, okay, where I've replaced the gradients with gradients along the unstable manifold. Okay, gradients along the unstable manifold are well defined, and there are also densities along the unstable manifold. Okay, as long as your measure mu is a physical measure of a chaotic system, and it satisfies this is a specific type of physical measure called the SRB measure. If this is your target distribution, you can take the formula for the score operator and treat it as a fixed point equation, fixed point iteration. Because if mu is indeed a physical measure, it is invariant by definition. So F push forward mu is mu. Okay. In addition, this G, the score operator, is actually going to be a contraction if you define the gradients only along unstable manifolds. Intuitively, you can think that if you take the gradient of F in the unstable direction, it's blowing up, right? So this inverse is going to be less than 1. And so this is a fixed point iteration on function space for calculating S mu. Okay. We used this in a linear response algorithm, but I'll point out that there are faster ways to do fixed point algorithms for the score that Angshu has come up with. Either way, basically you do a fixed point iteration for the score, And I would like to see this used for sampling, basically. So because it's a fixed point iteration, what it actually means is that if you take an orbit of a dynamic or chaotic dynamical system and you perform this computation, all of these objects are computable. Because if you have the dynamics, you can take its derivative in the unstable direction. You can calculate these unstable directions using standard Lyapunov vector computations. And so really just use this recursively to now obtain the score anywhere you want along an orbit. And this, because it's a fast algorithm, it's going to give you the scores along orbits. It's going to converge very fast. And hopefully this can be used now to sample. Once you have the scores, you can use it in a sampling algorithm. As for how to use it in a generative modeling algorithm, that's more complicated, but there is hopefully room with enough information about the score, something can be done to make generative modeling faster. So I just wanted to leave you with this as a remark to think about dimension reduction using these scores, which are easy to compute for if your target measure is the invariant measure of a chaotic system. Okay. So I will conclude here with a brief summary and references. So the last thing I said was that we can hopefully think about dimension reduction algorithms for sampling and generative modeling both settings in the case where our target measure is an invariant measure of a chaotic system by thinking about these projections on unstable manifolds. And then before this, I talked about, I'm going in reverse chronological order. I talked about adding this Jacobian term, this fundamental question of why this leads to statistical accuracy when the target measure is the invariant measure of a chaotic system again. Then the first part, this is more about target measures that have a low dimensional structure, may or may not be associated with dynamical systems, but we took a dynamical systems approach to study their alignment and characterize when they have this robustness of the support property. This part is not yet published and it is under review. I am happy to share the paper if you want. And then this on Jacobian matching is joint work with my student JJ Park and Nicole Yang from Emory University. JJ is at Georgia Tech. And then there are some ideas about transport maps in this joint work with Yusuf Marzouk and Florian Schaefer. But I haven't discussed that today. So yeah. Thank you. Thank you very much.
All right, thank you very much. Thank you. Any questions or comments? Yeah, Manjunat, you can unmute yourself.
Hi. Okay, sorry. If you're reading the question, it's fine. Okay.
Yeah, a good question. Am I assuming shadowing property holds for the underlying chaotic system? Yes. Yeah, so this is very restrictive. It's only for like some hyperbolic chaotic systems. If you have shadowing and the surrogate model has shadowing, yeah, you can basically show the surrogate model has shadowing. Yeah.
Right. So in case the underlying system doesn't have shadowing, can you show that the surrogate model has some kind of restricted shadowing, in the sense like the perturbed system belongs to only a certain class of perturbations, maybe a continuous perturbation or something? It's not just like any pseudo orbit, but an orbit which is like obtained from a continuous deformation of the surrogate model.
Yeah, so when the surrogate model is learned with the Jacobian matching laws and the original model has shadowing, then basically you only need the shadowing property to hold for the original model. The shadowing properties are
Yeah, I'm asking in the case, just let's not assume anything, any shadowing with the original or the underlying model. Okay. Suppose I build a surrogate model from the data, and will that surrogate model have restricted shadowing with respect to pseudo orbits coming from the perturbation of the surrogate model? So it's like not any pseudo orbit, but a pseudo orbit which is just like continuous deformation. So I don't know if I'm clear.
I see. You want
so yeah.
if can I repeat this question? Maybe I haven't understood.
Maybe if I were to just tell in terms of notation, say your original system is F, which is I'm describing it in terms of in the discrete time, which is a map. So you learn G, which is your surrogate model. And then I'm not using the same notation. My apologies for that. I missed a lot of, because of my connection, I missed a lot of your slides. So G is my surrogate model. Now I have H, which is closer to G by epsilon. So H has its own pseudo orbits. So will an orbit of H is a pseudo orbit of G. So will there exist an orbit of G? Sorry?
What is H?
H is your model close to G.
And F is close to
F
G.
is F is also close to G, but G is, we do not have a verification. How? Because if I have only data, then I do not know what is F. This is the very common practical case. You build a G. Okay. And then when you build a G, then I want to know if there is a nearby H, that is G and H are close by, epsilon close, then an orbit of H is actually a pseudo orbit of G.
Okay.
Now the question is there a true orbit of G, which is which epsilon shadows the orbit of H?
So this depends on whether you're basically asking if shadowing holds for G.
No, I'm not considering any pseudo orbit of G. I'm looking at a special case where the orbits are generated through H. I
see. You're not looking at, you only want shadowing for some specific orbit?
Yes. Because that is the most relevant case. We should not be really interested in getting all sort of orbits, because even if when you generate your surrogate orbit, surrogate system or whatever, you physically realize it or through a circuit or something, there will be some errors. So we want to know whether.
Yeah, so I can tell you a little bit about how to understand this for a specific orbit. So if you say, but I don't have a general answer. I'm just going to say something.
Thank you.
So, so if you take a specific pseudo orbit of H, right? Let's
pseudo
say
orbit of G, specific orbit of G.
Yeah. Sorry, specific orbit of H, which is a pseudo orbit of G. Then you can look at the differences between. So you can, the goal is to find a true orbit of G that is close to the pseudo orbit, right?
Exactly.
So then you can write now a sequence of vectors that tell you the difference between the pseudo orbit and the putative orbit of G that is supposed to be close. And you have to prove that this sequence of vectors exists and its norm is bounded independent of time, or like if you want a time that is for a bounded time, if you want shadowing, then you want to prove that the sequence of vectors exists and their norm is uniformly bounded in time.
I see. Okay, great.
To do this, so to prove the existence of the sequence of vectors, you have to look still at the Jacobian of G, the Jacobian matrices of G along this putative putative orbit of G.
Okay. Is there anything? Is there a reference that you can point out?
Oh yeah, there are the classical proofs of shadowing, and you can see if you can wrangle it to get.
Because the classical proofs, all of them rely on any pseudo orbit. So I was just looking at
but you can look at, like, you can try to restrict to like one pseudo orbit And then you simply, so in the classical proofs of shadowing, right, they consider the existence over vector fields.
I see. Okay.
But you can restrict yourself to some sequence of vectors and do some computation for that is orbit specific. But I'm not sure if every part of the proof will go through. Yeah.
Right. Right. Great. Okay, then. Thank you very much for the information.
All right, thanks. Any other questions?
Hi, I have a question. Can you hear me?
Yeah,
Yes.
Hi, Nisha. Very inspiring talk. Thank you. And I have a question about this Jacobian matching, because I've been working with a variation autoencoder architecture for reconstruction of orbits. Okay, so in the three-body problem, and so I think this can help me with my problem, because so I have my neural network for the encoder that is made of a convolutional or recurrent neural network, and I have my latent space, and then the decoder does the way back. No, it's actually something transposed network of these convolution layers. And I'm observing so the same, so actually some similar stuff that you showed in terms of lattice or reduced dimensional manifold that in such a encode the space of my orbits in this reduced dimensional lattice space. So now my question is, I want to improve the reconstruction of the orbits. And I'm interested in these Jacobian laws, in the sense that so the Jacobian in this case will be the Jacobian of the neural network that is only the decoder part, because I suppose this is the one that is acting in the form of the integrator. No, the one that we are using in that you've shown is basically acts as an integrator. Because I try to impose, I mean, to enforce a sort of physical laws, in the sense that I have my time series, so each state that is generated, and I compute the Jacobian of the dynamical equations, and I impose that to be so I impose the reconstruction of the derivative, basically, no? But
That's right.
okay, but here it is something different. So I impose that the Jacobian of the neural network matches the Jacobian, so the Jacobian of the decoder matches the Jacobian of the dynamics, basically.
Right. So if you have some, let's say your state space variable is x, and then you have some encoder, say E of x, and your decoder is acting, so it's decomposed with E of x, and you want to differentiate, you want to take the Jacobian of decomposed with E with respect to x and compare this to the real dynamics. So this is all Jacobian with respect to the state space. So I do believe you have to differentiate the decoder with respect to E of x, and then you have to differentiate E of x with respect to x.
So the entire network at the end is the Jacobian of the entire encoder and decoder.
Yes, I think so. Yes,
and match this with the with the Jacobian with respect to the each state of the trajectory. Okay, thank you very much.
Other questions?
Yes, I have a question about the existence of the classifier in the proof you were saying. But you said you assumed, but you didn't prove the existence of the classifier, right?
So if you have a, sorry, I went over this, didn't talk about it clearly. So when I say I have a convergent generative model, I mean that if you take samples from the generative model, so if you take samples from the true target distribution, you can find an optimal transport map that can take you to samples of the perturbed dynamical system. Because if you have a perturbation and your model actually converges, these two distributions are small in Wasserstein distance. Corresponding to that, there is an optimal transport map. Okay, So this comes from convergence results. I have not proved them. I assume that the model is convergent. So this is what I assumed. There are many proofs that if for a small epsilon, the obtained distribution p tau epsilon is close to in Wasserstein distance to p data. And there are also in Wasserstein distance, TV distance. Here I'm taking Wasserstein distance. Then if this is true, what I'm additionally saying is that for if you now take just these points, right, that there exists a classifier, which is a one class classifier that takes really the points from p data and gives you one if these points, if a new point is on the support and zero otherwise, like a classifier that generalizes using the real data. I believe this probably always exists. I don't know the exact conditions, but if you take like a finite number of points, there is like a one class kernel based classifier. So it doesn't have to be a linear classifier. It can be a non-linear classifier. So equivalently a kernel based classifier that takes the real points and tells you that generalizes to a new point. In that if you take a new point, it will tell you if it is from the same support as p data or not. Now that classifier is the same, the margin of that classifier will be the same as the margin of the classifier that is trained with y1 through m. If the classifier is trained with x1 through m and you get a classifier that generalizes, the same classifier, the margin of the classifier will not change if you train with y1 through m. That was the claim I was making.
Okay, thank you. So, and I want to also ask about the perturbation you presented for the images. So basically, you are perturbing the score, or you are perturbing the distribution of the data. So I didn't understand about that perturbation.
Got it. I'm perturbing the score. So
okay.
For in this example, for example, I take I have a pre-trained model that is generating the score, right? That is generating the digits. Now I take the pre-trained model and add random errors to this model at each time. Okay. So I'm deliberately saying this score is wrong and I'm adding something to the score at each time. So this is the incorrect score, and it can still produce an incorrect score can still produce something meaningful.
Okay, so you did the same with the bunch of ImageNet you were showing.
Yeah, exactly. That was not ImageNet, that was CIFAR10.
Yeah, CIFAR. Okay,
so
yeah.
Here also I did the same thing. This was a pre-trained model that was giving very good images from CIFAR10. And then I added perturbations of order 1. So I added deterministic vector fields that are order 1 in norm. L infinity norm for the vector fields is 1. And I still got these images. And I added them at each time.
Okay, wonderful. But do you are you open for if someone wants to work with you? Because what you are doing, I'm really interested in it.
I see.
Yeah.
I would be, thank you. Yeah, we could set up a Zoom meeting to chat later. If you could just send me an email. I'm available all summer, actually. I'm not traveling much, and yeah.
Okay. So basically, I'll need your email to send you an email.
Yeah. I will send you my email is somewhere maybe. Oh, sorry, I haven't written. I can send my email on the chat.
Okay, wonderful.
Chicago. Yeah.
Okay, thank you so much.
All right, thank you very much. I think any other questions? Nisha has been talking for almost 2 hours now.
I was hoping to not get close to your record. Yeah.
Yeah, well, my record is 2:30. You are welcome to beat it up.
No.
You're still 45 minutes far from it. Yeah.
Yeah. I feel safer. Yeah.
Yeah, but you did well. Yeah. All right. Any last questions or comments? Yeah, okay. Thank you very much, Nisha, and thank you all for coming.
Thank you all for
yeah.
coming.
Yeah, I probably have other questions for you, but I'll ask you by email as well. Yeah.
Yes, that would be great for me. Thank you very much.
Yeah, thank you.
Thanks, everyone.
Thank you. Bye. Bye.
Bye.